Welcome everyone to today's data science seminar. I'm David Bader, the director of the Institute for Data Science at the New Jersey Institute of Technology, and we're pleased today to have with us Dr. Charles Leiserson. Dr. Leiserson is the Edwin Sibley Webster Professor in MIT's Electrical Engineering and Computer Science Department and leads the SuperTech Research Group. He served as Associate Director and Chief Operating Officer of the MIT Computer Science and Artificial Intelligence Laboratory, CSAIL, the largest on-campus laboratory at MIT. He's the Margaret McVicker Faculty Fellow, the highest recognition at MIT for undergraduate teaching. He's a fellow of 4 professional societies, the AAAS, ACM, IEEE, and SIAM, and he's a member of the National Academy of Engineering. Dr. Leiserson has received many Best Paper Awards at prestigious conferences, as well as major awards, including the ACM IEEE Computer Society Ken Kennedy Award, the IEEE Computer Society Taylor L. Booth Education Award, the ACM Paris Konalakis Theory and Practice Award, and the ACM and Hertz Foundation Doctoral Dissertation Awards. Professor Leiserson's current research centers on software performance engineering, making computer programs run fast by whatever means: algorithms, parallel computing, caching, compilation, processor pipelining, bit tricks, vectorization, and so on. His contributions include the Silk Parallel Programming Language and Runtime System, which have been available in major compilers for over a decade. Today, he's speaking on software performance after Moore's Law.
So I'm delighted to join you, David, and New Jersey Institute of Technology. Great. So yeah, I want to talk a little bit about software performance after Moore's Law. There is some debate as to whether Moore's Law is over. I have my opinion about that, which I'll share. But regardless of whether it's over now or a little bit later, what are we going to do about performance? So always when I look ahead, the first thing I do is look back and try to understand in what way current times are analogous to today's time, and what has happened and where we're going. So let's take a look back at the early days of computing. So this particular computer, the RCA 501, was the first commercial all-transistor computer that appeared in 1958. It weighed about 5,000 pounds, had between 16 and 260 kilobytes of primary memory, core memory. The storage access time was 15 microseconds per byte. And it could do binary addition in 45 microseconds per byte. So it was a variable length word, essentially. But really, if I had to say in modern terms what the word size was, it was 1 byte, 8 bits. It had secondary storage, 1.5 megabytes of magnetic drum storage. And the Air Force purchased this machine for $121,698 in 1959. Okay, so over $100,000 this cost. But also, you can see here, it had up to 63 magnetic tape units and included 2 12.5-ton refrigeration units. And in fact, when the Air Force installed it, the floor had to be reinforced to support it. Okay, so that's when I was 5 years old. Okay, just for comparison, you can do the math. And in 1959, Dick Feynman, the Nobel Prize winning physicist, wrote a highly influential paper. He actually gave an address in 1959 that appeared in 1960 to the American Physical Association, I think it was, where he said there's plenty of room at the bottom. And what he meant by that, by bottom, was that you could miniaturize. And he talked about a bunch of different technologies that things could be made smaller without affecting them. And in particular, he also dwelt on computing because he had been the computing director at Los Alamos during the war, during the World War II. And he knew a lot about computing and about the need of physicists to compute. And he looked and he said, you know, we could shrink stuff. And we have been on a path towards shrinking. Now, a few years later, in 1965, Intel founder Gordon Moore forecast an economic and technology trend, okay, which we've come to call Moore's Law in 1975. We started calling this Moore's Law. It turns out that Moore's Law, there are several versions of it. If you look in the popular press and so forth, what they usually mean when they say Moore's Law is that the cost of computing drops exponentially year by year. And that's actually an implication of the real Moore's Law, which I'll get to in a moment. An example of that in my lifetime, I was the network architect for the connection machine CM5, which in 1993 was #1 on the world's most powerful. It was actually the first, top 100 list. Now it's top 500, but at that point it was top 100. And we were able to get the astounding performance of 60 gigaflops on LinPack with this machine. And it cost $47 million for the full configuration. Today, the Apple laptop that I happen to be using to make these slides and such cost $2,800, and it gets 120 gigaflops. And in fact, almost any way you can measure my laptop today, it exceeds what we could do on the connection machine in 1993. In fact, this iPhone is in many respects more powerful than that supercomputer, the #1 computer in 1993. It's really astounding what Moore's Law has brought us. Now, had Moore's Law ended 15 years ago, there's all kinds of technology we would not today be enjoying. Everything from things like electric cars to deep learning. A lot of people say, oh, deep learning, wow, what a tremendous revolution we're having. You have to ask, whenever you see a revolution, why didn't it happen earlier? Turns out the algorithms were there. There were two innovations that caused deep learning. One was the availability of large corpuses of labeled data. That was huge. But the other thing was unprecedented amounts of computation that didn't exist when some of the algorithms had originally been devised. So computation was a hugely important part of this. And there's all kinds of other things that have come along over the last 15 or 20 years. The one my daughter is particularly interested in is Minions. We would not have these fabulous animated movies that artists can make today. Now, the original Moore's Law was a projection made based on 5 data points that Gordon Moore laid out. And he said the complexity for minimum component costs has increased at a rate of roughly a factor of 2 per year. In ordinary English, he was saying the number of transistors has been doubling every year. And based on that, he plotted a plot up to 1975. What has come to be known as Moore's Law, however, is not this, because Gordon Moore, 10 years later, said, you know, it's actually doubling every 2 years rather than every year, he felt, by the end of the decade. And actually, if you plot the transistors on microprocessors and you do a curve fit, it is a factor of 2. It's not a factor of 1.5 or anything like that. It is a factor of 2. Now, there are other technologies that have accelerated as well. And in fact, memory size has gone a little bit faster than the traditional Moore's Law. But Moore's Law for processors is basically has been doubling every 2 years. Okay, and the impact of that has been that we get cheaper computing, more transistors, and it's been a printing press for processor cycles, because you can use a lot of those transistors to make things go faster, and you can also use them to make there be things like multi-core. But this is the thing that is ending, okay, or has ended, depending upon your point of view, okay? We are not able to sustain this rate of doubling the number of components every 2 years. Now, the demise of Moore's Law has been predicted before, okay? And why is this anything? In fact, one of my favorite quotes is from Peter Lee of Microsoft, who said, the number of people predicting the end of Moore's law doubles every 2 years. Okay, so, but in order to understand what's happening, it's important to understand, you know, where we are. So we see where we've been. We started out with these mammoth machines weighing tons, okay, and taking up rooms of buildings and so forth, down to, oh, I fit something more powerful in my shirt pocket. So where are we now? Well, let's see. A few years ago, in 2014, Intel achieved a feature size of 14 nanometers. Now, 14 nanometers is small. It's 140 angstroms. 140 angstroms. Remember what an angstrom is. Angstrom is what you use to measure the width of things like atoms and such. Okay, it's really tiny. And they hung out at 14 nanometers for a little while. Okay. In 2015, Intel announced that, well, things weren't quite going to be on the schedule they had planned for improving Moore's law. The way that Intel works when they're making processors historically has been that every year they have 2 events. One they call a tick, the other they call a tock. A tick is when they do the shrink. This is when they take the existing design, essentially, and shrink it to make and produce a chip with the same architecture as they had for the previous generation, okay, but twice as many components. That happens every 2 years. And then what they do is they take the transistors, and on the top, they redo the architecture to better take advantage of the existing technology. So rather than just using the old technology, the old architecture, on a TOC, they leave the feature size the same, but now they improve the architecture. And what they did in 2015 is they said, whoops, we're going to have a tick-tock-tock. we're going to revise the architecture twice rather than delaying the shrink. Okay, so and some people say, okay, that's the end of Moore's law. Well, maybe. Intel said it wasn't. And most of the press said, oh, no, 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 it's going on. But if you actually look in February 2016 at the official forms that they have to file with the government, okay, in particular, Securities and Exchange Commission, where they're under great penalties if they lie to possible investors and so forth, because they're a public company. Hidden in this document is they say, we expect to lengthen the amount of time we will utilize our 14 nanometer and our next generation 10 nanometer process technologies, further optimizing our products and process technologies while meeting the yearly market cadence for product introductions. Okay. That effectively is confessing that Moore's law is over, because Moore's law is not just miniaturization. It's miniaturization at a rate. That's what Gordon Moore contributed over what Feynman had said. Feynman said there's plenty of room at the bottom. The question is, can we maintain the same rate of miniaturization? Okay. Now, Feynman is also that things are going to bottom out as well. But Moore's law is about, can you keep doubling every 2 years? Because that's what we've been doing. Okay. And then in 2018, oops, their 10 nanometer technology is broken. It's delayed until 2019. Okay. This was their next shrink. Okay. And then finally, on August 1st, 2019, Intel finally announced their first 10 nanometer, which is 100 angstrom process. So their density doubled in 5 years, not 2, nowhere close. So to my mind, Moore's law is over by this definition. Okay, now Intel will say things, and a lot of people who promote, oh yeah, we're still going, they're talking about miniaturization increasing. And yes, we will continue to miniaturize, but not at the rate we've been miniaturizing. Okay, our ability to get free stuff out of our silicon is slowing considerably. There's still some there, but it's slowing considerably. Okay, and I'm reminded in a lot of ways of what of the comedian Stephen Wright. I don't know if you know this deadpan comedian. He is full of what are called one-liners, which are actually 2 lines. But and I love this comment by Stephen Wright. He says, "I intend to live forever. So far, so good." Okay, and many people treat Moore's law as, oh yeah, it's going fine. We're not gonna, it doesn't have to be over. Okay, yeah, well, people have solved the problems before and so forth. Well, turns out, yeah, we've confronted a lot of issues, confronted the problem with the photolithography, that we couldn't do things with light, and we had to start doing them with e-beams, electron beams, and a variety of other obstacles along the way. Okay, but now it looks pretty convincing to me, okay, that the party is ending, but we're having such a good time. Okay, why does the party have to end? Okay, so the first basic reason is because of physics. And here's the kind of fact that nobody has a great answer to. Okay, it's just implausible without some major breakthrough that semiconductor technologists can make wires thinner than atoms, which are at most a few angstroms across. It's just like, how do you conduct electrons if you've got no thing to conduct them on? Okay, maybe you can do it by telekinesis or something. Okay, but No, we don't know how to do this. Okay, how to conduct things. It's not on anybody's plan how to do that. Although, in the by the way, this is a great opportunity for researchers in this area because you can do things that sound really great. Like I saw one a news announcement that they had made a wire of single atoms, and therefore Moore's law continued. Okay, it's like, well, that says you can miniaturize more. It doesn't say we're at the same rate of miniaturization. And then it's like, well, one atom. Okay, well, what's next? Half an atom? I don't know. In fact, the silicon lattice constant is 5.43 angstroms. That's the rate at which the atoms, which the crystal repeats. Okay, so there are a few more in there, but really they're pretty small. And most technology roadmaps, they will show you that feature size keeps decreasing. But essentially at around 5 nanometers, none of them that I have seen show any projection that the size of transistors themselves will shrink. Okay, so you can shrink some of the feature sizes, the minimum feature size, but then you look at how big are the various things you're building out of and it's like you're sort of stuck at 5 nanometers. But as I say, the historic Moore rate has already attenuated. Okay, we're not doubling every 2 years. Okay, so that's 2 shrinks from 10 nanometers, which is where Intel is right now. It is maybe you get a 3rd shrink, I don't know. Maybe even a 4th. Wow, but you're talking about things the size of atoms. Okay, things change. Materials don't have their properties when at the subatomic levels. They only have their properties because of their aggregation. So this is really, really weird. Okay, now you may see other things like TSMC will tell you that, oh, my goodness, they're already past 10 nanometers, but their measurements are different from Intel's. So that's a marketing thing. Okay, they're pretty comparable. So for example, TSMC's 10 nanometer process was actually very similar to Intel's 14 nanometer process. So you got to be careful about how people are labeling these things. It's, a lot of it is marketing. Yeah, I'll name my process even smaller than what other people name theirs. And then look, we're ahead of the game. But the other reason is economics. Even if we could push semiconductors a little further, it becomes prohibitively costly to do so. You can push things below, down and down, but it starts getting more and more expensive, as well as taking longer and longer to do. Okay, and that's why my view is that we're not going to see a return to double the density. Even when people talk about things like 3-dimensional, they're not talking about the number of layers that they're going to put on these chips doubling every 2 years. They get a couple more layers, maybe every 2 years, maybe. And so that's all, folks. It's like we're not going to get a lot more out of semiconductor technology without some dramatic change. And so people say, oh, but what about quantum? So quantum has made pretty incredible strides, actually, but it's still in its infancy. It's not like the 55 years of semiconductor improvements that we've been having with Moore's law. Okay, today's quantum computers incorporate at most a couple thousand qubits, okay, not billions. Now, in fact, each qubit can represent and so forth, but really they're not general purpose computers either. They're good for what we found is some search problems and so forth. Okay, they are not demonstrating yet that they are ready to take where we are and move it by 2 years, by doubling every 2 years. And they already use state-of-the-art lithography. So they can't ride miniaturization. So what trend are they riding? And if you look at other exotic technologies, they exhibit similar drawbacks. Okay. So as far as I can tell, no exotic technology is ready to rescue Moore's law. We are not going to get more performance, okay, more of this printing press out of Moore's law. Okay. And so I could end the talk there. Okay, everybody goes home and cries and so forth. But I actually want to talk to you about the fact that there are things on the horizon. I want to talk about one in particular, which is software performance engineering. Okay, so this is the cavalry coming to rescue the besieged people. That may be politically incorrect, I guess, but it is a cultural thing that the cavalry comes to rescue people. Okay. Last summer, I had an article appear in Science magazine called "There's Plenty of Room at the Top." And I want to mention this article and then take you down one path of it. There are 3 paths. So let me explain a little bit what we mean by the top. So by the top, we mean the top of the computing stack. So when Feynman said there's plenty of room at the bottom, he meant in physics. As opposed to big things, there were small things. We're actually returning to the original term, which was there's plenty of room at the top. This is a phrase that, or a statement that Daniel Webster made when he said, when somebody asked him, why are you going into law when law is so crowded? And he said, there's always plenty of room at the top in any profession. Okay, so so here, though, what we mean by top is the computing stack. And the bottom, we mean things like semiconductor technology. And you build up our current systems. And near the top, you have things like software and algorithms and hardware architecture. The very computer science things, as opposed to very physical and electrical and so forth. Okay. And in particular, we identified software, algorithms, and hardware architecture as 3 areas where we saw wonderful opportunities to keep making performance improve. But we argued that the performance was going to be opportunistic and such. And so what I'd like to talk to you about today is the software end of this, because I think there's wonderful opportunity to look at where we are and what can be done, because I believe this is a big area. This is, of the things you can do in software in particular, is we can redress a legacy of excess, okay? So this is kind of like, many software applications today have an enormous amount of bloat. For what they do, they don't do it very efficiently. In some ways, you can kind of view what I'm doing as, okay, we created all these systems as computer scientists that had all kinds of bloat. Okay, and then we're going to promise to people, okay, now we're going to solve their bloat problems. This is kind of like the, the fireman who's also an arsonist, and he sets the building on fire and then comes to rescue it. So that's kind of what we're doing here. Okay, we're actually going to be in a position to rescue it. So We're not going to get performance improvements from things like Moore's law, but we can engineer the performance of our software to produce opportunistic, uneven, and sporadic gains. So it won't be broad-based, it won't be everywhere, but there are a lot of places you can get a lot of performance. I want to illustrate that with a problem that we demonstrated in this science article. So here is a code for doing matrix multiplication in Python. Now I know that you can call a library that'll do this thing already, but somebody had to write that library. But I want to use this because most people understand matrix multiplication, and they understand that but what I want to do is not focus on the matrix multiplication aspect of this, but if you were to write this in the naive way in Python, okay, yes, you could optimize this by calling another function. In fact, doing that is called performance engineering, okay, where you call a library that does it fast. But often you have something like matrix multiplication, but not exactly matrix multiplication, where now you have to do it yourself because the library doesn't do it for you. And now you're in the same position you would be as if you had matrix multiplication, but no library. And that's the illustration here. So here's the code, okay, that I'm going to be interested in benchmarking, okay? And the important parts of this, the first part is just pulling in the, creating two random matrices to multiply and initializing the output. And then the key part is that there's doubly nested loop. And here I'm going to use n of 4096. So 4096 by 4096, about 16 million entries, very small matrix for the size that people solve these days. And you say, go through the familiar triply nested loop and do the inner product sum. Start a timer before, start a timer after, okay? And I'm going to use a, what at that time was a pretty good machine for doing this problem. Okay, it was a C4 8X large spot instance on in the Amazon cloud in AWS. This is a dual socket Intel Xeon processor that has 18 cores. Its clock speed is nominally at about 3 gigahertz, and it's got a lot of DRAM, okay, 60 gigabytes, I guess they call that these days, right, of primary memory. And remember, we're only doing something that's got, 16 million entries, and if you multiply that times 4 for the double precision, each matrix is only 64 million entries, okay, and we've got 60 billion bytes. So, okay, and remember, n is 4096. Okay, so how long does this code take to execute? Okay, does it take 6 milliseconds, 6 seconds, 6 minutes, 6 days, or 6 hours, or 6 days? And the hint is that there are actually 128 billion 64-bit floating point operations. So for curiosity, David, can you now, do I have to stop share or can you just share directly?
I'll just load the poll.
Okay, you do the poll. Here it goes. Very good. Okay. So which of these is the closest? Can you see the summations here, as people are voting?
Yes. Do you see the sums as they come in?
I don't see them.
Okay, so I see about 60% of their audience has voted, maybe about 2/3 right now, and 75% has voted. we'll wait another 10 seconds and then we'll stop the poll.
Okay.
We have a lot of bets in. Okay, so your last chance to vote.
Okay, just take a wild guess. I mean, it does. When I guessed, I was way off. So.
Okay, so we have 86% of our audience voting. That's 44 people, 45 people, and now we'll end the poll. And I'll share the results.
Wow, it's pretty evenly distributed among the first things. Okay, so how interesting. So in fact, the plurality got it right. Okay, it's in fact about 6 hours, 5 hours and 50 minutes is what it cost to execute this. Okay, now is that good or is that not so good? Well, we decided to try to make it better. And so we went through a series of improvements to the basic algorithm. So the first version is the 21,000 seconds, which is the Python. And I'm going to have relative speed up is basically the speed up compared to the previous step. So we went through a series of 10 steps here. We actually went through more, but I'm putting the 10 major ones. And absolute speed up is what we get over that first implementation. And the next column is how many gigaflops you get, and then percent of peak. The percent of peak is actually an underestimate. And one of the reasons for that is the way we calculated the peak was we assumed that you could run all the processors at full speed. And in fact, you can't due to things like DVFS and turbo boost in the Intel hardware. It slows the clock period down as you get more processors operating, et cetera. But we still use that as our measure. Okay. Now it turns out that just simply recoding into Java, same code, okay, gave you a factor of 8.81 speed up. Just recode it in Java. Don't use Python. Use Java. And if you just recode it in C, okay, you get another factor of 2 speed up or so. Okay. If you interchange the loops, okay, because it turns out that's not the best order for the looping, okay, you can get, in fact, a factor of 6.5 more performance. And then if you set the optimization flags for the implementation to make sure that it's doing all of the things that the compiler could possibly do, you can actually get a factor of 3.25 out of just setting optimization flags in the compiler. Okay, and so at this point, we're actually a factor of 385 faster than our original code. Now, it turns out that none of these languages use parallelism. Okay, so let's throw in some parallelism. So you do a parallelism, and you get a factor of 17.97 more. Okay, it's like almost a factor of 18 more. And then if you optimize memory a bit using tiling, you get another factor of 1.7. Okay. And then if you actually do parallel divide and conquer, which uses the memory system, it turns out even better, you get a factor of 1.38 better. And then if you vectorize use compiler vectorization, okay, you can get a factor of almost factor of 2 more. And then if you actually look carefully at the inner loop and recode it, essentially using assembly language, using the AVX intrinsics, you get another factor of 1.76. So in the end, you're less than 0.4 seconds. Okay, so really, really very much faster. And that represents an absolute speed up of over 50,000x compared to the code that you originally wrote. Okay, now you might wonder, this we actually did with Python 2.79. Okay, and so we reran this test, by the way, when Python 3 came out, because after all, it's later, it's, you know, better. Weren't using the best software of the day to do this. When you run this with Python 3, it takes almost 9 hours. And that makes sense. They're delivering productivity to people, but at the cost of performance. But the fully optimized matrix multiplication program contains over 20 times more lines of source code than the original Python program. And you're sort of in this dichotomy here where if you want to have your code be really simple, it tends to be slow. And if you want it to be fast, it gets complicated. And that's where we sit today. Okay, not that everybody sits there. A lot of people are interested in this problem, but that's kind of a choice that a lot of people have to make today. You want it to be, you know, fast? Well, it's going to be complicated. You want it to be slow. And so for after Moore's law, I think, you know, my research agenda, and I would like to advocate that it should be a lot more people, is let's have a vision. Let's make a world where it's easy and fun to write fast code. Okay, where you don't have to have this, you know, this choice. And the idea is that right now we do performance engineering in a rather ad hoc way. Okay, it's a bunch of tricks. There are some principled things along the way, but an awful lot of it is let's just try this and try that and so forth. And if you master this huge bag of tricks, you can optimize one thing. But this is far out of the reach of average programmers. And it is also something that is not very principled. It is just something where, okay, you do this large, complicated number of things. My research group has been working on that. And one of the ways that we've been working on that is we have developed a task parallel programming system called OpenSilk. So many of you may know about Silk, which is a parallel programming platform. We have recently gotten the Air Force and the National Science Foundation to fund some infrastructure development for OpenSilk. Okay, and the idea is to provide systems that are going to have this kind of, not where people don't have to make these choices quite so starkly. Okay, I don't think this is the only way of doing it, but I think it's an important way of doing it. And interestingly, we are addressing both application developers and the parallel language researchers, as well as teachers, because we want it to be simple for the teachers. Okay, most parallel language systems today, you're addressing either the application developers, they address the application developers, and then the systems are so complicated inside that you it's very hard to do research on them. Or the parallel language developers have much smaller systems that they use, but they're not real world systems. They're things that you can demo. And the goal of OpenSilk is to hit both bullseyes, make it something that people can use for application programming and make it simple enough that parallel language researchers can invest in. We have 4 main components in it, plus a lot of surrounding stuff, including libraries and benchmarks and so forth. Those are the compiler, which is based on the Taper LLVM technology that won PPOP Best Paper Award a couple years ago. We have a runtime based on Cheetah, which Angelina Lee contributed. The compiler was essentially done by TB Charlotte. That effort was led by TB. We call him, it's Tau B, but everybody calls him TB. It includes compiler-based tools of a race detector and a scalability analyzer, so you can predict the performance of your things. Okay, and I'm very happy to announce this is the first talk that I have given since OpenSilk version 1 was released last month. Okay, and you can get a copy of it, you can play with it, you can do real stuff with it. If you have been using Intel Silk Plus, the conversion should be very, very simple. And you should be able to, with just a couple minor modifications, be able to run and get better performance right off the bat, because we have a superior compiler. Okay. I'll mention also, by the way, that David Bader is on our OpenSilk advisory board. So we've tried to get top people around us to give us good advice as to how we should evolve the system, which is what we're currently in the process to do. And let me also mention that we're looking for postdocs. So if you know of people who like to do this kind of system development for high performance infrastructure, we're very interested in you. And in particular, we're very interested in people who are interested in helping build tutorials and educational materials and so forth. Now, we've kind of identified 4 cornerstones of doing science-based and performance engineering, which we've tried to embody in the things that we've done. The first one is systems that you can reason about from a performance point of view, because the performance obeys simple mathematical properties such as monotonicity and composability. So monotonicity is things like, gee, if I take work out of my application, shouldn't it go no slower? May not go faster, but shouldn't it go no slower? Turns out that's violated all the time, okay, by many systems. And composability. Okay, I build a program to do something and I build another program and I combine them. Oh, it doesn't work very well anymore. This was fast, A was fast, B was fast, but A plus B is not fast. Okay, and so OpenSilk has that kind of composability of performance where something like OpenMP does not. When you do 2 things, you call a library, you call 2 libraries in parallel, and they both thrash the use of the processors, et cetera. We're also interested in theories of performance that work in practice. So you can do things like asymptotic analysis and work span analysis and using the ideal cache model and back of the envelope calculations. Okay, that those should allow you not to have to build something to discover that, oh, it doesn't go any faster. Okay, you should be able to predict these things before you go on a big engineering thing. We are interested in diagnostic tools for correctness and performance whose efficacy is mathematically grounded. And our 2 tools, Silk Scale, which is the scalability analyzer, and the race detector, have that kind of property where they will predict what is going on for you and tell you what's happening. And very importantly, reliable measurement and ubiquitous instrumentation. Okay, and for that, we have a subsystem called CSI, for Comprehensive Static Instrumentation, that is not in OpenSilk to begin with, but we hope to get it there at some point in the future. We're actually using it internally in things like SilkScale and SilkSAN. We're not quite ready to release an API that we promised to support. And this last one I think is really important. So you may remember Lord Kelvin, who was introduced measurement to physics. And his moniker was "to measure is to know." And he said, if you cannot measure it, you cannot improve it. My understanding is both of these are paraphrases that he never said, but you know, the web is great for misinformation. But anyway, it applies. And if I hadn't told you it was not necessarily so, you probably would have believed me. Okay. So is there life after Moore's law? Well, I think the end of Moore's law will elevate the importance of performance engineering. We can make a world in which performance engineering is tedious, unpleasant, and boring, practiced by high priests with arcane knowledge. That's where we're headed. Or we can make a world in which performance engineering is engaging, creative, and fun, practiced even by average programmers. That's what I want to try to do. Okay. To do that, software developers have to become educated in the principles and practices of science-based performance engineering, which unfortunately two people today understand or appreciate, but I believe that's something that all the universities should be thinking about. And that completes my talk. I'd be delighted to answer any questions. If possible, take the questions that refer back to my slides first, and otherwise we can go to like a gallery view would be good. And I'll stop the share.
Thanks, Charles. There's a bunch of questions coming in, but let me just reminisce a little bit, because your talk reminded me that the very first conference I attended where I presented a paper was PPOP in 1995, over 25 years ago. And I remember, I think it was Bobby Blumoff who gave the original talk on Silk there with you. And it really changed my view of parallel computing and performance. And it's just an honor to serve as an advisor on OpenSilk right now. And it's just been fantastic to see the progress over all these years.
Thank
so
you.
we have a lot of questions and comments that have come in. And so if others have questions, please put them in the chat and we'll try to get to them. And I'll just start on one of these from Marcin Paprzycki. Long time ago in the world far away, Cray YMP had Fortran compilers that could do miracles with one's code. It seems that people will always write mediocre codes, and it's the compiler that should do the job for the average programmers. Thoughts on that?
Well, I would love if there were an automatic, means of, to be able to do things, and we do everything we can. But typically, improvements in compilers leave you a few percent. Okay, they do not do things that require an incredible amount of creativity because they don't really understand your intent. Okay, and so, when it comes to like, oh yeah, let's automatic, for years people studied automatic parallelization, which I think is still worth studying. And I think still there is stuff to be mined there. But you can't expect a compiler to do anything that you can't do yourself. Having worked a lot on compilers, one of the things you learn about compilers is that before you write the compiler code inside the compiler to do something, you have to hand compile it yourself so that you know what the transformations are going to be. Well, how can you hand compile it yourself if you don't know what's going on? Okay, and you can do things like, yeah, these technologies come out, but they are moving stuff so much slower than people move. Oh, let's do machine learning to make everything go faster. It's like, yeah, but machine learning really is good at things like classification. Okay, it's statistics. It's not creativity yet. Hopefully we get there someday, but right now, that's a big distance. So yes, it would be great if you could write sloppy code, it would figure out what you really meant by it and give you, quick sort when you wrote insertion sort.
So when we programmed, say, 20, 30 years ago, performance was always a key because resources were very limited, memory, compile time, and the space that we had. And nowadays, that really isn't much of a consideration to current programmers. How do we take current Python programmers today, which now exceed C programmers, I believe, and get them to understand the headroom of what they're leaving on the table versus the performance that we could get out of these great processors?
Well, I think, my experience with these things is it takes people a while to do stuff. It takes them a while. And this is not going to turn around on a dime where Moore's law ends and suddenly. So first of all, Moore's law ends. How long does it take for people to notice that it's end? Okay, you just keep doing the same thing. Okay, and then what happens? It takes, 10 years later, it's like, wait a minute, we should have had 3 doublings by now. 8 years later, right? Okay, wait a minute, we're not, where did that go? Okay, and I think the other thing is that people, this will happen in segments. So for example, if you talk to Intel, not Intel, Google, they want performance engineers. If you talk to the hedge funds, they snap up the students out of my class like crazy because they know how to optimize codes. Okay, they know that happens to be an area where if you can compute faster, you get an advantage, immediate. So those kinds of skills, I think, are coming up, but we don't make it easy for people right now. And I do believe that, we are turning. So the point is, for young people, this is a good wave to catch. Be there early when people aren't thinking about it so much. It may be a little bit more struggle starting than if you jump into machine learning. Okay, so you jump into machine learning, it's like, wow, there's a lot of jobs and stuff in machine learning. That's great. Okay, all for power to them. But what is going to happen down the road? Are you, what's the growth potential in the area? Whereas in software performance engineering, it's like people want performance. Performance is the currency with which we spend, which we buy other properties. We use performance to buy usability. The reason we have Python is because we have so much performance to spend. We can afford to spend some of our time on programmer productivity, some of our computing on programmer productivity. Okay, this is one of these paradoxes. It's like, why if which would you rather have, David, a $100 bill or a gallon of water? Okay, well, there are circumstances where you'd prefer a gallon of water, like if you're out in the desert with nothing around. But for the most part, in a modern society, you much rather a $100 bill because for $1, you can buy a gallon of water. Then why do people want money as opposed to water? Water is essential to life. Well, economists answer that by saying, look, it's not what's important, it's supply and demand. Okay, you can buy the water with $1. So I'd rather have $100. I can get the water that I need. Okay, and in some cases, you can argue that the prices go up and so forth, but it's not about which is more essential or anything. Performance is like that. You can spend performance to get many wonderful properties. Okay, you can say, okay, I'm going to do error checking on my code so it's more maintainable. That will cost me some performance. Okay, yeah, that's great. I got performance to spend. I'll spend some performance on that. Okay, there's a lot of places we spend performance on usability, on graphics, on all kinds of things. That's why we want it, because we can spend it.
So that's a great answer. We have so many questions on the chat. I'm not sure that we'll get to all of them, but we'll try to ask a few more. One question that came in from Alan Young, who said, "Great talk. Do you have any books to recommend on software performance engineering?"
Well, I'm trying to write one. No, it's really scattered. It's really scattered. There isn't, I think, a good, the best ones were written years ago. So one book is John Bentley's Writing Efficient Code.
Yeah,
Writing efficient programs. That's
that's a great book, and
unfortunately it's just completely dated.
Correct. I still go back to read that book every 3 years or so, because it's wonderful. I have to convert, megahertz to gigahertz and
right,
kilohertz to gigs, but it's a great book.
It's a great book, and he had the right idea and so forth. And I think that that book was one of the early important things in performance. I think another one was Knuth creating the first code profiler.
Mm-hmm.
Okay, what a monument in performance engineering. Like, oh, let's measure our code. Oh, look, you're spending a lot of time on just a few instructions. You don't have to optimize every instruction. You can go for the inner loops and the recursive functions that are called a lot.
You may be familiar. A number of years ago, Kathy McGill, who was at Amherst, now D-Wave, wrote a great book on one-topic algorithm engineering, which also has some nice case studies and points in there.
There are a lot of things like that around. I certainly cover a bunch in my class, which I'm trying to turn into a textbook, but I have a 4th edition of another textbook that has to get done first.
I see 3 right behind you.
Yeah, we're right now working on the 4th edition, which goes to the which has to be put to bed. Right now, the copy editor is working on it, and we're working on the copy editor's comments, and that we have till the middle of May to get, and then it will go into production and be available in the fall for teaching.
Great.
So algorithms.
That's great to hear. What a great book. We maybe have time for 2 or 3 more questions. On the Zoom is Weiwei Jia, who wants to ask a question.
Thank you. Thank you, Professor Charles, for the great talk. So I have one question. May I know your opinion about what are the software performance bottlenecks after Moore's law?
I would say that most software today is not parallel. Okay, so the key players, they make sure their stuff is parallel. Google and Facebook, et cetera. They're all doing, parallel. But average people, average applications, it's not parallel. And if it is, it's been parallelized rather badly. That's certainly one. I think, we don't have great languages that give you both high level programmability and good performance. An exception there is Julia, which has a lot to recommend it in terms of being getting much of the best of both worlds.
So do you mean the parallel program today are not efficient, right?
Writing parallel programs is really difficult. Okay, it's really difficult.
But according to my experience, understanding, most of the programs in clouds and data center are multi-threaded. They are run parallel on multi-cores nowadays. Yeah. So they already be
running on. That's what I say is that the big players can do that. But if you want to write a program for a particular purpose, it is, it's an arcane art. Most software, if you look at what runs, so yeah, let's say if you go to the top end, you're going to find a lot of parallelism. Indeed. Go to the the Google App Store or the Apple App Store, okay, you will not find many parallel programs there.
Okay, got
Okay?
it.
You won't find them, okay? And here's the thing is that a lot of them are trying to do things that are going to stress the need to use the available processor capability. They want to do things like language, and they want to do things like machine learning and so forth. Okay, so yeah, if you go to the high end, you can see some of this, but that's rarefied, and of course, in the, we're always attracted. Oh my goodness, there's, there are all these things that are using, a lot of things. I'm really impressed, for example, with Guy Blelick's work in this area, where he went and looked at one of these systems that was using 500 cores on 30 machines or something. I don't know, and to accomplish this thing. And then he showed you could do the same with a little performance in engineering. You could do the same thing with a Mac Mini.
Okay.
Right? I mean, it was like, yeah, you can do that. And and there they were doing, it was distributed, et cetera. It's like, no, a Mac Mini was enough to do this.
Okay,
And-
got it.
So,
Okay, thank you.
I want to thank everyone who attended, and there's a lot of great questions, but I think we're out of time, and we should wrap up now. But Charles, thank you so much for a great talk. Very stimulating.
Thank you for inviting me. It's always a delight to talk to audiences, and especially ones that had such good questions. I wish I could have handled more.
And I hope everyone will pick up OpenSilk 1.0 and try it out. Take care.
Tell us how bad it is so that we can improve it.
Thank you so much. Take care.